So welcome everyone to our public lecture. So the public lecture of the Department of Mathematics. We're very glad that we could put this event together and have such an illustrious speaker. We're also very glad that you could all come. I can assure you that he gave an excellent lecture yesterday in the math department, so I'm sure this will be just as excellent, if not even better. So our speaker, Kevin Buzzard, is a professor of mathematics at Imperial College London. After his undergraduate studies at the University of Cambridge, which made him a senior wrangler, he received his PhD also from the University of Cambridge under the direction of our now colleague, Professor Richard Taylor. So a reunion in this way. He is a recipient of a number of honors, including the Whitehead Prize of the London Math Society and the Senior Berwick Prize of the LMS. Since 2017, so apropos this lecture, since 2017, he has been involved in a formalization of mathematics project, which let him give a special lecture in the 2022 ICM on the use of formalization and the rise of formalization in mathematics. So he's going to expand or go beyond maybe on this.
Well, a lot has happened since then.
Yeah, a lot has happened since 2022. And so I would like to ask you to welcome Professor Kevin Buzzard.
Yeah, so thank you very much for coming out. Thank you very much also for the invitation. I do a lot of gigs nowadays, but I mean, they're not all Stanford. So I'm genuinely honored to be here. And so I'm going to talk about AI I'm going to talk about some aspect of AI. So yeah, what can AI do? And one thing that AI can do now is, as you know if you live around here, is that AI can now drive a car. And AI driving a car, that's sort of 20 years ago, that was complete science fiction. So that's sort of absolutely amazing that AI can drive a car in some sense, but actually sort of hundreds of millions of humans could also drive cars, right? So in another sense, the fact that AI can drive a car is actually not particularly remarkable because we already know, somehow, we already know how to drive cars. So great. So now machines can drive cars. So this talk isn't really about machines doing things that humans can do. This is some of the hundreds. It's not the case that hundreds of millions of people can do this, right? This is these professors in the math department at Stanford, many of whom are actually in the room. The question is, this is a much more specialized task, being a math professor at Stanford. And the question I want to talk about is it reasonable to expect that AI can do what they can do? So this is what the talk looks like. There's going to be 25 minutes of what does a mathematician actually do anyway, because I'm assuming that you're not all math professors at Stanford. And then there's going to be about 25 minutes of how are computers maybe going to fit in with this. So, what can computers do? Can computers help mathematicians? Can computers beat mathematicians? That sort of thing. And then there's 2 slides at the end, speculation about the future. So yeah, so first section, what does a mathematician do? A mathematician does mathematics. And what's mathematics? Well, it's what a mathematician does. And so let me show you some mathematics. So I'm going to have to talk about numbers, because that's definitely one of the things that's supposed to be covered. So I'm going to go with the easy kind. I know there are other numbers. Other numbers do exist, like pi and square root of 2. But when I say number in this bit, it's just going to be the counting numbers. So 1, 2, 3, 4, 5. And I'm going to talk about prime numbers, because that's one place where it really gets interesting. And so just to remind you what a prime number is a number. 1 isn't a prime number for some historical reason or something. Sometimes it was a prime number, but currently 1 isn't a prime number. And then all the numbers bigger than 1, some of them are prime and some of them are not prime. And the way you can tell is can you break it up as a product of 2 smaller numbers? So for example, 6 is not a prime number because 6 is the product of 2 and 3 are both smaller than 6. But 5 You can't, 5 isn't 2 times anything. Well, I mean, it is 2 times something, but that something isn't a number in this section. So 5 is not a multiple of 2 or a multiple of 3 or a multiple of 4. If you want to break up 5 as a product of 2 things, it has to be 5 times 1 or 1 times 5. And they don't count because 1 is smaller than 5, but 5 isn't smaller than 5. So 5 is a prime number. So here's another way of thinking about prime numbers, is that you could look at the multiplication table that we were all forced to learn as children. The first row, like the nth row is the n times table, right? So the 7th row is 7, 14, 21, the 7 times table. But the first row is the 1 times table. And that row, if you continued it on forever, that would have all the numbers in it. And similarly, the first column has got all the numbers in it. So we have to remove the first row and the first column. And when I decided to do this, I didn't have much of a, I had to, sorry. I removed the first row and the first column. And what we've got now is all the numbers which are sort of interesting. They're not 1 times something, they're like 2 times something or 8. Yeah, let's find it. There's 63 there. That's going to be 9 times 7. So all the numbers you see there, that's sort of all the numbers that aren't prime. And then so the prime numbers are what's left if you look at the multiplication table. So there we go. So now we all know what prime numbers are. Great. So why am I waffling on about prime numbers? And the answer is the prime numbers, like, if you're a chemist, you say like every molecule, matter is comprised of atoms. And that's kind of an important thing in science. And in mathematics, similarly, you can build every number from prime numbers. Prime numbers are the atoms of number theory. So let me give you an example. Let's take a random number. So the current year, 2024, let's break it down into a product of prime numbers. And the first thing we observe is that 2024 is even. So it's when all numbers bigger than 2, which are even, they're not prime numbers. So this is definitely, 2024 isn't going to be a prime number because it's 2 times something. And you figure out it's 2 times 1,012. And 1,012 is also even. And so we can take out another factor of 2, which is twice 506. And 506 is also even. So we take out another factor of 2. And then we get to 253, and 253 is odd, so our trick no longer works. And so it could well be prime. Is 253 prime? Well, we'll go on then, factor it. Anyone dare? Yeah, exactly. 11 times, I knew it, nerds, you see. That's what you get. That's what you get with stat. Exactly. 253, as everyone who knows their 23 times table knows, 253 is 23 11s. But 11 and 23 are prime, and so we have now broken up this non-prime number into a product of primes, and so you can see that prime numbers are like atoms. Okay, so now we've got questions about prime numbers. First question, how many prime numbers are there less than 10? Any volunteers? 4. So there you go. There's the prime numbers less than 10. There's 2, 3, 5, and 7. Okay, harder question. How many prime numbers are there less than 100? Anyone happen to know that? I've got you. 13. No, it's more than 13. 25, you see. Yeah. This talk's going to be over in half an hour. I reckon I just get you to get. There are 25 prime numbers less than 100. Excellent. A quarter of the numbers less than 100 are prime. So it's 100 divided by 4. Where did that 4 come from? And here's how, we'll just quickly check that there's 25 prime numbers less than 100. There's all the numbers from 1 up to 100. And now we have to isolate the prime numbers. And actually, there's quite an efficient way of doing this called the sieve of Eratosthenes. And I'll briefly show you how it works. So for some reason, 1 is not allowed to be a prime number, so we cross it out. And then the next number, 2, is a prime number. So we'll keep 2. But all the other even numbers, all the other multiples of 2, we can get rid of them because they're not prime. So there we go. That took ages to do, with a mouse as well. So apologies. So I should have prepared it anyway. So we've crossed out all the numbers, all the multiples of 2 that aren't 2, because none of them are prime. And now let's look at the next number. It's 3. So 3 is prime. And then and some of the multiples of 3, like 6, we've crossed out already. But there's loads of multiples of 3, like 15, that we haven't crossed out. So we cross out all the multiples of 3 that were still around. And now 4 we seem to have dealt with. 5 is the next number. 5 is prime, but all the other multiples of 5 are not prime. And then 7 is prime, but all the other multiples of 7 are not prime. and they were those. The first time I did this, I got this wrong. And then we have to count what's left. I should say, and that's it, because any number, if you've got a number between 1 and 100 that isn't prime, then it's the product of two smaller numbers, and those numbers one of them has to be less than 10, right? If they were both bigger than 10, their product would be bigger than 100. So you know if it's got a factor, one of the factors must be in the first row, and we've done all the numbers in the first row now, so we can stop now. And now you can count what's left, and if you count, you get 27, and you realize that you've got it wrong, and then you kind of go back and you realize you didn't cross out 91. And anyway, I've got it right now because I counted, and there's 25, and it's been confirmed that there are 25 numbers. Okay, so next question. You know this one? How many prime numbers are there less than 408,000? So that's not the kind of question that we want to be evaluating in this lecture, because that's not the kind of question. That obviously that's the kind of. I just showed you a method, right? This is the point. I showed the moment there's a method. What happens at school? We just spend forever at school teaching kids the method, and then they do the questions. These questions are extremely boring, right? That question's extremely boring, and one of the reasons it's boring is we've got a method for it. And so you just routinely, it's like multiplying 4-digit numbers together. You apply the method, and you get the answer. And there you go. So really, we don't want to do that by hand. Well, I mean, we want to use a computer. And in fact, the reason I went with 408,000 was, in fact, historically, this was the first time this question was resolved. It was solved by a computer, and in the late 1700s. So, sorry? No, it wasn't Gauss, but Gauss was like 17. It could have been Gauss. It was a guy called Felkel, Anton Felkel. And he wrote, we've got a picture of him there. There he is. And there's his device here. He used this device here to work out whether a number was prime or not. It had sort of 8 moving rods, and you can Google how this thing works. So this is the front page of Felkel's treatise, which he was claiming that he was going to factorize every number between 1 and 10 million. So that was the original aim of the volume. But he only got as far as 408,000, and then he might have seen sense or something, I don't know. But for some reason, things petered out. So this was volume 1 that went from 1 up to 144,000. And then by volume 3, he got up to 408,000, and then the other volumes weren't ever published, as far as we know. And there's one of the pages from volume 2, which is yeah, I had a look at this book. It's quite an interesting book. So this is exactly halfway through, 204,000, half of 408,000. And what he did was he wasn't interested in numbers that were multiples of 2, 3, or 5. If your number, you've got a number and you want to break it up into primes, then you don't have to work it out. You don't have to know that 253 is 2311. So the idea is you look it up in his book. But he didn't want to cover all the even. There was pointless doing the even numbers. So if your number was a multiple of 2, 3, or 5, you were expected to spot that yourself and divide those factors out by yourself. And so he only did the numbers that weren't multiples of 2, 3, and 5. And so the top number here is 204,001. And that line there, what is this? It says EMU. It says EMU. So I'll tell you, maybe I'll tell you this is what's going on. 204,001 is not a prime number. It's 7 times 151 times 193. But he didn't want to write those numbers in that box, so he had a code, you see. So E is 7, because 1 was a prime back then, you see. So A was 1, and E was 7, and then we've got M in a different font, and that was 151, and then U is 193. And then 204,002 is a multiple of 2, so it's not in the table. 204,003 is a multiple of 3. The next one is 204,007, and that is a prime, and so that gets its own, so now it's called that funny letter there. So weird capital something. I don't know what it is. There's some German letter, I don't know. But so that's a prime. So every prime had its own letter, you see. And then 204,008, that's even, so it's not in the table. Next one was 204,011, and that was M type. Wait, we had M already. M was supposed to be 151, but this is M in a slightly different font. And so that was how it worked, and that was how the book worked. So there you go. So now the question is, so that was what research mathematicians were doing in the late 1700s, and now what does a research mathematician do in 2024? And of course, this is one thing they don't do, is they don't work out all the prime numbers less than 408,000, because we've got machines to do that now, right? So humans don't need to do that, and this is what, technology advances, and then mathematicians change. They change their behavior because they don't need to do some questions anymore. I'll come to why we were interested in how many primes there are less than 408,000 in a bit. But technology advances and mathematicians adapt, and they start doing the jobs that technology can't do, right? Okay, so here's another question: how many prime numbers are there? And that's a question of a different nature, right? Because somehow the answer to all the other questions was like you sort of count them, and it's sort of a finite job. But how many prime numbers are there? Like there sort of could be, I don't know. Well, like let's do what mathematicians do. Let's do an experiment. So here we are. Let's fire up a computer algebra package, and now for p is 1 up to a large number. Let's say if p is prime, then let's print p, and if p isn't prime, let's do nothing. And we hit that there, and there we go. And we've already beaten Felkel, sadly. It took him 18 months to write that book. But yeah, there's technology. So, and there seems to be a lot of prime numbers, right? And so we don't. So there is evidence. This is evidence that 100 million. So we've got up to 100 million, and they're still good. So this is evidence that there's infinitely many prime numbers. I think we better stop doing that now, or I'll run out of batteries before the end. So based on our experiments, we're now going to conjecture that there's infinitely many prime numbers, right? And of course, if this is true, then the kind of things we were doing before, sort of working stuff out manually or on a computer, the techniques that I've shown you in this talk aren't going to work, right? Because this is a different kind of question. How many prime numbers are there? A computer can't calculate the answer to that question. But even long before the idea of a computer had even occurred to humans, Euclid 2,000 years ago had nailed this question, and it turns out that our conjecture is correct. There are infinitely many prime numbers. And I'll show you why this is true. What I'm going to do is I'm going to show you that if n is a number, then there must be a prime number that's bigger than n. And that will do, right? Because if there were only finitely many prime numbers, then there'd be a biggest one. And if you let n be the biggest one, then there aren't any prime numbers bigger than that. So all I have to do is give you some kind of recipe, whereas if n is a number, I need to find a bigger prime number. And now comes a brilliant idea where you take n factorial add 1. So you multiply all the numbers from 1 up to n together, you get a gigantic number called n factorial, and then you add 1, and this is now a molecule, so it breaks up into atoms. So there will be one or more prime numbers that go into this big number n factorial add 1. So you take one of those prime factors, and I claim that that prime factor must be bigger than n, because if it was n or less, then it would go into n factorial, and by its definition, it goes into n factorial plus 1. And prime numbers can't go into two consecutive numbers, right? Like you don't get an even number and then another even number next to it. You sort of have an odd number in between. Even numbers are spaced out by 2. And so the multiples of a prime p will be spaced out. There'll be p numbers between each one. So a prime can't go into two consecutive numbers, so this prime number must be bigger than n, and that's the proof that there's infinitely many primes. And that's what mathematicians do, right? We don't do stuff that computers can do. We prove theorems like that. So that's what a mathematician does. It looks for, the mathematician looks at what we know, the mathematical landscape or the Platonic universe or whatever you want to call it, and they try to discover new structure. And this is a two-part process. This is the first thing they have to do is to kind of figure out what the right question is. So they look at an area of mathematics, and they try to sort of they try to find the structure that that is hitherto hidden, and once they spot that new pattern, then that's called making a conjecture. So you're sort of guessing about what the mathematical landscape looks like. And maybe you've done that because you've got a lot of data and you've realized that the data is supporting a conjecture. Or maybe you're just one of these people that sort of stares at the ceiling and sort of thinks about things very abstractly and can come up with ideas even without examples. Such people do exist. And I think they're really incredible people, to be honest. I was always interested in trying to compute examples. Even when I was working with very complex mathematical objects, I was always interested in trying to write down examples of these objects. But not every mathematician does that. So making a conjecture is sort of guessing what's going on in the mathematical landscape. And then, of course, sometimes you don't make the conjectures, you try and break the conjectures. You try and solve them. You try and prove the conjectures, just like we saw this proof by Euclid. Once you prove the conjecture, you've turned it into a theorem. So those are the things that mathematicians do. And this is not what you see at high school at all, right? This is a long way from there being a method. You see, this is the art. This is the art of, this is where the creativity comes in. And this is, in some sense, it's quite sad that many people leave school having absolutely no idea what mathematics is really about. But beyond some point, mathematics becomes an art. And so that's the end of section 1. And now section 2, of course, is can computers do that kind of thing? I mean, we know they can compute all the primes up to 408,000, but can computers, be artists? Can they make conjectures and can they prove theorems? So what does a proof look like? Well, I showed you a proof, and the proof said something about infinity, right? The proof touched infinity in some way. The conclusion of the proof was that something was infinite. But the proof itself wasn't the proof was definitely a finite object, but it wasn't a calculation. It was something else. It was like the solution to a logic puzzle. So finding a proof is like solving some kind of puzzle, and you can formally express that. In fact, you can write down what the rules of mathematics are, the axioms of maths, and you can write down what the rules of logic are, and then you can completely frame a mathematical proof within the context of creating an abstract mathematical structure using these rules whose conclusion is the theorem you're trying to prove. And so this is, computers, of course, computers are very good at manipulating numbers. They can multiply gigantic numbers together. But because a proof is something completely different, computers are not going to be able to prove theorems apart from the fact that this is just complete nonsense, right? Computers can play chess. That's got nothing to do with numbers. Like anything where you can write down what the rules are, you could teach a computer the rules, and then a computer could, in theory, learn to do that thing. So if you're used to computer algebra packages, then you know that computers can manipulate numbers, but there's no reason that computers shouldn't be able to manipulate proofs in theory. And there you go. That's a computer program, which you can run on sort of specialized software. And what this computer program does is this computer program corresponds in a very concrete way to the same proof that I showed you, that there's infinitely many prime numbers. And you can see some of the steps I skipped. I said that we've got this number n factorial plus 1, therefore it must have a prime factor, but actually 1 doesn't have any prime factors. So you need to check that n factorial plus 1 is bigger than 1, and you can see that's there about a third of the way down. And you see, even though this is about the infinite, a proof is a finite object, even though it's proving that something's infinite. And so, a computer might be able to understand that proof. So the kind of computers that most mathematicians use are computer algebra systems. We thought that I was using a computer algebra system to work out how many primes there were. And they're very good at manipulating numbers, but computer proof assistants, you can have variables that correspond not to numbers, but to theorem statements and to theorem proofs. And these things exist and are usable in 2024, and a proof corresponds to a program, and if the program compiles, that means your proof is correct. So as I say, the code on the previous slide was written in a proof assistant called Lean. There are many proof assistants around, but the one I use is called Lean. And the thing about that proof was that just like Euclid's proof, that proof was not written by a computer, right? That's absolutely something I want to stress. This proof that this proof that there are infinitely many prime numbers, you take the human proof that we know and you manually translate that proof into the language of the computer proof assistant, right? So this is not, these computer proofs, they're not solving the problem. They're not doing mathematics autonomously. But what they are doing is they're checking, they're checking mathematics. So is that actually useful that we have a, I mean, because mathematicians, you know, they're very smart people, so they really need, and they check each other's work, right? We have a refereeing process. And so is it actually useful to have some kind of a system which can check your work for you? And the answer is yes. And here's Terry Tao, one of the world's greatest living mathematicians, really. And he decided that he would learn how to use this software. And so he took one of his recent papers that he put on the internet, and he translated it manually himself into this programming language. And at one point in his proof, he has a half times log n minus 1 over n minus k minus 1. And the computer pointed out during the translation process that a completely valid value for n at this point in the argument was 3, and a completely valid argument for k was 2. And so the denominator becomes 3 minus 2 minus 1, which is 0, and he's divided by 0. And you're not allowed to divide by 0 in mathematics. And this was up on the internet, and people had read it, and no one had spotted this. And he types it into the computer, and the computer instantly spots they divided by 0. So the actual message he posted on Mastodon is twice as long, so I'm doing him a disservice because I've cut off half the message, and the second half of the message is explaining how it doesn't really matter that much, and you can modify the proof, and he's going to upload a second version. And like, you know, the theorem was still basically correct, although some of the numbers had to be modified slightly. So in the actual full post, Tao goes on how to fix the problem. But if these things are sort of better than a Fields medalist at checking, these, I mean, one can argue whether these things are perfect, but what's certainly true is when it comes to checking mathematics, they're superhuman. They are better than every time. I've used this system a lot, and I translate the literature manually, and every time the system complains, and it says that, you know, there's something wrong, every time the system has complained, the system has been right, and the human has been wrong. So they are superhuman when it comes to checking. Right. Last question about prime numbers. How many prime numbers are there less than x? Do you know that one? Yeah. Very good. So how was that? Do you know how that was discovered? So I'll tell you then. So Felkel computed all the primes up to 408,000, and Legendre, another mathematician around that time, that gave him the data he needed. Right? So you can't, you know, obviously the answer is it depends on x, but the question is, what does the function look like? You put in x, and you get the number of primes less than x. So Legendre was able to do experiments up to 408,000 in the 1790s. You know, so it was 100 divided by 4 was the number of primes less than 100. And so the question is, for x, what do you have to divide x by to get the number of primes less than x? And you can tabulate that because you've got all this data. And Legendre realized it was x divided by some mystery number. And that mystery number, according to the experiments that we had up to 408,000, that mystery number looked a bit like log x. And this is, as has already been pointed out, this is not log to the base 10, because prime numbers don't know about how many fingers we were evolved to have. This is natural logarithm to the base e. So the number of primes less than x is x over log x. So this was conjectured by Legendre at the end of the 1700s, and Gauss independently realized that this was the case. Gauss did not have access to the Gauss worked this out by staring at the ceiling because he was a genius, but Legendre needed the backup of the data. So there you see sort of two different mathematicians doing things in two different ways, but coming to the same conclusion. And this is a profound conjecture because I started off just talking about counting numbers and prime numbers, and that's that's discrete mathematics. But the logarithm function, especially the natural logarithm function, does not belong to discrete mathematics at all. This is a continuous function. So this conjecture relates the discrete to the continuous. So it must be a sort of a profound. You start with prime numbers. How the heck are you going to get to? That's nothing even to do with real numbers, let alone the logarithm function. So there must be something profound going on here. And the conjecture remained open for 100 years, and it was proved in the late 1800s independently by Adamar and de la Vallée-Poussin. I mean, there are many, many theorems about prime numbers, but this was regarded as sufficiently foundational that nowadays, I don't know what it was called before the late 1800s, but now it's been proved. It's known as the prime number theorem. So I'm not going to prove the prime number theorem, but I want to highlight the life cycle of the prime number. I want to talk about the life cycle of a theorem. So let's start with the life cycle of the prime number theorem. And the life cycle was that humans collected the data, and then humans looked at the data and made the conjecture, and then humans proved the conjecture. Okay? And so, of course, pre the advent of the digital computer, this is exactly what all mathematics look like. All pure mathematics look like this. And then computers arrived in the 1950s, 1960s. Mathematicians had access to these computers, and the workflow was changed slightly. So the Birch and Swinnerton Dyer conjecture, I'm not going to tell you even the statement of that conjecture, but this is one of the Clay Millennium problems. So this is, if you solve this conjecture, if you prove this conjecture, you get $1 million. And the history was that Cambridge got its first computer in around 1960. The EDSAC-2 is one of these things. It was like the size of a large room and sort of had orders of magnitude less memory than your phone. But that's what they looked like in the 1960s. And during the days, they were being used to do the calculations that became modern tectonic plate theory. But it was discovered quite early on that it was a really bad idea to turn the EDSAC-2 off. Because if you turned it off, then when you turned it on, when the geologists arrived the next day and wanted to do their tectonic plate thing, when you turned it on again, like some of the valves would blow, they'd explode. And they realized after a while that it was sort of more cost efficient to just leave the thing on all the time. So the geologists would go home, and at 5 o'clock, Swinnerton Dyer would sneak in with his punch cards and get the computer to just do these very mundane calculations of counting solutions to equations, to cubic equations in two variables modulo prime numbers. And him and his collaborator, Brian Birch, they got this huge amount of data that they've got to make some kind of sense of, and eventually they drew the right graph. And when they drew the right graph, they saw the pattern, and the moment they saw the pattern, the conjecture was born. So, and as it happens, this one, I mean, we still made, especially over the last 20, 30 years, we've made substantial progress with this conjecture. And it really wouldn't surprise me if I got to see a proof of this conjecture in my lifetime. I remember in the 90s somebody pointing out that this was definitely 21st century mathematics. But here we are, a quarter of a century in. It's still open, but I do feel that progress is being made. So what's the lifestyle of the Birch and Swinnerton Dyer conjecture? Well, now computers were involved, right? Computers did the mundane task of collecting the data, and then humans had the insight and made the conjecture. So this was hard work, right? You didn't just look at it and it was obvious. But eventually they arranged the data in the right way, and they realized what the conjecture should be, and they made the conjecture, and it turned, I mean, in 20 years' time, it could say the humans proved the conjecture. But currently the conjecture is still open. And so that's how things worked from the 1960s. So obviously there were still humans making conjectures. So some conjectures were discovered by humans without any computer input, but some conjectures now, they're discovered by computer calculations are sort of guiding you along the way. So that's how things looked until 2021, and then 2021 something else happened that I'm about to explain, where the life cycle was different again. And the key thing that happened was the neural network. So right, what's a neural network in 2 minutes? Well, somehow at school in statistics, I learned the concept of a best fit line. You've got data, you've got your temperature, and the amount of ice cream you're selling, and that gives you a bunch of discrete dots in your 2D plane. And then the question is, now you've got a day when it's 21 degrees, and you want to work out what your sales figure will be, but you don't have a dot by 21. All you've got is other dots, but you've got the dots, and they kind of look like they're on a line, and so you draw the line, the best fit line. I mean, you could do it by eye, but of course there's formulae for this sort of thing. You draw the best fit line through this data, and now you can work out if the temperature is 21, you can sort of conjecture how much profit you're going to make that day. And that's the best fit line. And the point of the best fit line is you can extrapolate your data to places where you don't have data. You can sort of guess what the answer is going to be anyway. So what's a neural network? In some sense, it's just a powerful generalization of the best fit line, right? So one difference is the best fit line is in 2 dimensions, but now your data can be very, very high dimensional. I'm going to talk about a 10-dimensional example in a minute, but you can have hundreds or even million-dimensional data. And it won't just find a best fit line, it will happily find a best fit surface or a best fit 8-dimensional object. And it doesn't have to be a line either. It can be some sort of best fit shape. So there's a very it's some kind of very brief one-slide summary of what a neural network is doing. And so that's the tool that we have now, and we've had for a few years. And now the question is, can we apply that tool to the life cycle of a theorem? And the theorem I'm going to talk about is a theorem in knot theory. And so what's a knot? This is an object the mathematicians study. It's you take a piece of string, you tangle it around, and then you join the ends together, and you've got a knot. And all of those 4 pictures are different if you look at them carefully. None of them are exactly the same, but each of those knots, you can sort of take the string and manipulate it around and change it from one figure into another. So all of those knots are the same. They're different pictures, but all of the same knot. And this knot is called knot 7-2, and mathematicians have got a system where knots are called numbers, some kind of numerical system. And the idea is, so here's a standard question about knots. Is given a knot, can you unravel it without sort of snapping the string? Can you unravel it so it's just like a circle of string? And one way to prove that you can't unravel a knot is you discover a knot invariant. So the idea is you attach a number to the knot, and you make sure that even if you jumble the knot around and so it looks different, you still get the same number. The number doesn't change if you sort of move the knot around in 3 space. So there's knot invariants, and various knot invariants have been discovered as of many different kinds. Some of the invariants are whole numbers, and some of the invariants are real numbers. Humans have discovered several genuinely different techniques to attach numbers to knots. And once you've discovered such a technique, you can then say, well, actually, given this knot, how do you work out the number? What are the invariances called? The volume of the knot. So how do you work out the volume of the corresponding hyperbolic 3 manifold or whatever? And of course, you can write computer programs that will work out these invariants. You work out a way of typing the knot into a computer by decomposing it somehow into a string of data, and then the computer will work out the number for you. And of course, computer scientists, they write code, or computationally able mathematicians write code that compute all these invariants, and they stick it up on the internet and make it free and open source. And then other people take computers and they write, if you actually got a specific knot and you want to work out some of these invariants, instead of having to actually run the code yourself, you can just look it up. You just look it up in a table. So these tables are up on the internet, and there's a page from the Knot.info website, and here the lists here. So this table is huge, right? There's not that many columns, but there's many rows, and each row corresponds to a knot. There's 7-2. That was the knot I showed you earlier. And this column here, you probably can't read any of these things. That says signature, and the signature of the knot 7-2 is -2, and that's its volume, and the volume is 3.331. So even if you have a knot, you don't even have to compute the invariance yourself. You can just look it up in the table, and there's the knots. So here's the ridiculous story about knots. So in 2021, an unlikely collaboration between a low-dimensional topologist obviously studies knots because they're one-dimensional. So 2 low-dimensional topologists in Oxford and 2 computer scientists that worked for a tech company, DeepMind. They did the following experiment. What they did was, firstly, they took the code that would generate these knot invariants. So they took about 10 knot invariants, and then they ran the code on some super fast computer for quite a long time, and they generated a gigantic table of invariants of knots. So it was about 1 million knots they had. So they've got a big table that's got 1 million rows and 10 columns. And then the idea is you've got that data. So that's far more data than Birchall, Swinton, and Dyer had. You've got like 10 million numbers now. And now the question is, where's the pattern? And the game is to try and find. And so, I've said that the neural network will try and find patterns, but how does this work in practice? And this is quite clever. There's this trick. What you do is, first of all, you take 10% of your knots and you cross them out. Or you take them away, you keep them secret. So 10% of the rows of this gigantic matrix of knot information, they take 10% of the rows away, so now we've got 900,000 rows and 10 columns. And the question that they asked the neural network, do you remember I told you, like, you find the best fit line, and then given the temperature, you can guess the sales, right? So it's just the same here. Now you've got these 10 columns, and for each column, you then cross out, you say, find me the best shape that fits through, that predicts, we fixed column 7, and now we want to predict column 7 from the other columns. So find your best fit shape in this huge dimensional object, and then the idea is we'll tell you 9 of the numbers, and you're going to predict the 10th one. So you train the neural network with 90% of this data, and you choose a column, and you say, OK, we're going to guess what this column is. And then you train the network, and the network says, OK, I've got it. I've got some formula internally that will guess. You give me the 9 columns, and I'll guess you the 10th one, right? And so the output of the neural network is a function that's actually there on your computer, and you can type in 9 numbers and evaluate the function, and it will give you the 10th number. And the thing is, the function is a formula, and the formula is completely incomprehensible. This is the big problem with neural networks, is we don't really understand what they're doing. So the formula it's like hundreds of pages long, and it's sort of a completely meaningless thing. And furthermore, so we don't really understand the formula, but that's what the neural network gives us in 2024, incomprehensible functions. But you can still run them, you just can't understand them. And now, of course, what you do is you test it on the remaining 10%. So just in summary here, what we've got, we cross out a column, we train on 90% of the data, and we ask the network to predict the missing. We ask the network to predict the missing number, and we tell it the answer 90% of the time, and then we start asking it the question. And if you take one of the rows that the thing's seen before, and you say, here are 9 numbers, what's the 10th one? It just gets it right every time. Because the thing about neural networks is if they've seen the answer already, they'll remember it. So you ask it one of the lines it's been trained on, and it gives you exactly the right answer. And then you ask it what the answer is for one of the hidden. You've got one of these rows that you never showed the computer, and you type in the 9 numbers, and you ask it what the 10th number is. And typically, you get an answer that's no better than random. So typically, the experiment fails. But what happened in this particular case was that for one of the columns, the experiment didn't fail. For the signature column, the very first one, the integer column, it turned out that the neural network with very, very high, not 100% accuracy, with very, very high accuracy, when you ran this incomprehensible function on that 10th column, it guessed the answer correctly. Not always, just with like sort of 95% probability. So what we have now is we have a completely incomprehensible conjecture that's not even right. It is right most of the time. So it's sort of useless in some sense. But what it actually is not useless at all, because what it's telling you is that there's something going on that we haven't spotted yet. That's the point. It tells you that something, it's giving you information that there's something to be had here. And because in particular, it's telling you what to look for. And you can do even better. Now you do a saliency analysis. Now what you do is you do something even more crazy. You change one of the numbers, you start fiddling with one of the numbers, and you leave all the other numbers the same. And now these numbers don't even correspond to a knot. So you do something completely weird. You change one of the numbers, you leave the other numbers the same. You change one of the inputs, and you see if the output changes. And you just keep fiddling around with one of the inputs, and you got one of the inputs, and you just keep changing from like minus this to plus this, and the output doesn't change at all. And you realize that actually the neural network doesn't even care about that input. even though that input no longer even, that vector of numbers no longer even corresponds to a not. So it's quite a weird thing to do. So you do this saliency analysis, and you work out which of the inputs are actually the important ones. And they realized that 3 of the invariants were the things that were actually controlling the signature, and the topologists managed to come up with a conjecture that was, this is not the function that the neural network came up with, because this is a function that fits on one line, as opposed to one that takes 100 pages. But the idea was the computers said that there was some kind of relationship, and then the humans looked at what it was and found out what the relationship was. And so this was the conjecture, but then within a few weeks, it turned into a theorem. And it's just like the prime number theorem. It's very surprising because this sigma is the signature of the knot. This is the slope of the knot. That's an integer. The slope is a real number. The volume is a real number. The injectivity radius is also a real number. So again, it's surprising because the signature is an integer variant. So it's somehow a very different nature to these geometric invariants coming from the hyperbolic 3 manifold, coming from the knot complement. So that's sort of interesting. So what was the life cycle of this theorem here? We've got post 2021. Here's a possible life cycle for a theorem: is the computers generate the data, but then computers, there's this new step now. Computers help the humans tell them where to look, and then the humans find the conjecture, and then the humans prove the conjecture. So you notice that it's like, so computers are sort of invading from the top, right? But it's still all humans at the bottom. But that wasn't just a one-off. It's happened now several other times. The person in the office next to me, one of their PhD students managed to pull this off. They found some pattern in tables of Fano varieties by doing exactly the same thing. They managed to get a neural network to predict an invariant of a Fano variety, and then they realized that if the neural network could do it, then there must be something going on. And then they found a new algorithm to predict this invariant that was like orders of magnitude faster than the ones that were currently being used. So story so far is we're beginning to see computers do 2 different things. Firstly, they check mathematicians' proofs, and they help them find conjectures. But that's great, but actually what's the real holy grail? What do we really want? What we really want is a machine that can actually prove theorems by itself, right? So I haven't talked about proving theorems by itself, and that's the last thing I'm going to talk about, because that would really be, at the minute these systems are helping, right? So that was the first, can computers help us? But, can computers beat us? That's the next question. So let's talk about language models, because I haven't mentioned them yet. So this is ChatGPT, stuff like this. So this is also a very recent revolution, and the question is, can we use these language models like ChatGPT to do mathematics? And the answer is right now, in 2024, they're not particularly good by themselves. So if you've used them, at the beginning it was sort of a bit of a joke because they were sort of laughably bad, but now they're getting better. But now we're sort of beginning to learn how they can be used to do mathematics. So a language, what you want to do is ask it very general questions, like how might I attack this problem? Which other areas of mathematics might I be able to use when attacking this problem? If you start asking them very general questions like that, then they can sometimes give you surprisingly insightful answers. Or sometimes they can give you answers that you know are wrong, but sometimes they can, you can brainstorm ideas. But the thing you can't start doing is asking them technical details because they have no understanding. They're not thinking in any way. They're just sort of parroting what you see on the internet. So they're no good at the technical details, and of course that's what this is all about. And what is confusing is you will think, actually, hang on, if I ask ChatGPT to prove there's infinitely many primes, it will just give you a perfect proof. And that's the same reason that these not things could generate, they would always get they've seen it before, right? If the question's in the training data, it always gets it right. It's when you leave the training data that things immediately become very ropey. So if you ask ChatGPT to solve a problem whose answer isn't on the internet, for example, an unsolved research problem, then it starts confabulating. A lot of people say that it starts hallucinating, but my partner Tamsin tells me that the correct word for this is confabulating. So It confidently asserts stuff which isn't true. Like hallucination is something else, right? Hallucination is taking LSD and looking at my trousers or something. I don't. But confabulating is sort of confidently talking about things that simply aren't true, but you sort of believe they're true. And of course, confabulation is not allowed. That's not one of the rules of mathematics. You have to actually stick to the rules. But earlier on, I mentioned this. I showed you some code which corresponded to a proof of the prime number theorem. And that code was written in the language of a computer proof assistant. And so let's compare computer proof assistants and language models. The language models, they're very, very good at writing. They're very good at writing text by themselves. They're completely autonomous when it comes to text generation. Unfortunately, they're not 100% accurate. They're error prone, and you can't have errors in a mathematical proof. And that's the exact opposite to these computer proof assistants, because they're manually powered. These proof assistants are not solving theorems by themselves. You physically type things in. Humans are doing this, writing the code, but they are superhumanly accurate. And so that's interesting, because we have two sort of powerful and independent systems which have appeared in the last few years, and the weakness of one is the strength of the other. The language models are able to write by themselves, and then the proof assistants might be able to check. The idea is, can we glue them together to make some kind of system which proves conjectures all by itself? And a few years ago, this is one of the sort of stupid, hypey things that all the computer scientists said was definitely going to happen, and it sort of sounded like a load of old nonsense. And of course, the reason that it's an interesting question is, if it does happen, and we get some kind of system backed up by a proof assistant, then mathematicians might have to adapt again. If technology can start doing the really interesting parts of our job, then that's a little bit scary. So here's the standard example that probably many of you will know about, the International Mathematical Olympiad. This is for sort of, it's a high-powered, difficult problems that you can solve using school-level mathematics. So every year there's sort of 6 extremely hard math problems, but this is for school children, so it's not using fancy research-level maths. This is, you can answer the questions using sort of high school level techniques. And DeepMind, again, the same company, they put Lean, the proof assistant, and their own language model, some Google Gemini variant thing. They put them together, and they tried it on the 2024 International Maths Olympiad. And these are not questions that were in the training data, because these are new questions that are sort of invented specifically for this task. And if you'd asked me beforehand what score they were going to get, I would have confidently said 0. And it got 3 of them right, and that's really quite surprising. And so it wrote, and it's not so they got it half right, but there was one little mistake, and so you give it 6 out of 7 or whatever. The language model wrote code in Lean, and then you run the code, and there's no errors in the code, and so you can really prove that these things have solved the problems correctly. So now, life cycle of an IMO problem, humans write the problems, computers solve the problem. So that's the first time we've seen in a life cycle, that's the first time we've seen computers at the bottom. Computer solves the problem. So, but the thing is, these problems, you don't need research-level mathematics techniques to solve these problems. You only need the kind of mathematics that sort of smart, that high schoolers have been taught, that advanced high schoolers have been taught. So what's going to happen next? Well, next year the same thing will happen, except it'll do better. Next year or the year after, it'll get a gold medal, or it'll get 100%, and then that'll start going on sort of university level competitions like the Putnam, or there'll be but you will not be surprised that some company will come along and they will feed it some sort of final year Harvard or whatever, or Stanford quals, or some hard undergraduate level problems, and it will solve the problems. That's absolutely there's absolute certainty that will happen. And then they'll start going on that their system can get a Stanford degree. And, you can decide whether or not that makes any sense. And again, remember, it's just the same. It's not. There are lots and lots of people that can get Stanford degrees. Like Stanford are churning out many people every year with Stanford degrees. So in some sense, it's not that great. So that's what will happen, and a lot of fuss will be made. But anyway, so the DeepMind, right? The DeepMind works closed source, so we don't really know what's going to happen. But one big problem is the lack of training data. But what apparently the system did was it took each IMO problem and then it generated 1 million. So this is what they say in the blog post. It generated 1 million similar problems, and then for each of those 1 million problems, it sort of tried to prove them and it tried to disprove them, and some of them it proved and some of them it disproved. And it did this, and some of them it got stuck on, and somehow beyond some point it tried to, it sort of got some feeling as to sort of the shape of the problem in some, again, these things are very good at finding patterns in high-dimensional data. They understood somehow the shape of the problem, and we don't really know what's going on, but that's some estimate as to what's going on. So I've got 1 minute left, but that's great because I've got 2 slides left. So I've been speaking a lot about facts because I'm a mathematician, I'm a fan of facts. But I've got 2 slides of speculation. And one thing I've noticed is that you tell these stories to mathematicians and they say, yes, but yes, it's not a big deal. Everything that happens is like, well, yes, of course they can do that. So I'm sort of becoming skeptical when I hear mathematicians say, well, these all the time, whenever anything big happens, they're like, well, yeah. But, that could have happened years ago and it's not really a big deal. But I personally am quite happy to admit that I was quite shocked as to what happened in July. I would have definitely guessed that everything was going to get 0. But of course, we can try and explain it away because it's kid stuff. It's school-level mathematics being put together in a very clever way. It's not at the boundary of modern research. So the big question is, will the ideas scale? Will what we've seen scale? And will computers start making their own conjectures? Because we've seen them help humans make conjectures. Well, in 5 years' time, will they be making their own conjectures? And will they be turning them into theorems automatically? Because if they do, then we as mathematicians need to be slightly concerned. And if you talk to the computer scientists, they'll tell us that it's not without good reason that we should be concerned. But now let's try and extrapolate from the data we have. This is last slide. What's absolutely clear, the one thing that's kind of weird, and it wasn't true before, is that all of a sudden tech companies have got their eye on what we're doing. And that never used to be the case. The tech companies were typically interested in other questions. But the idea is a few years ago, they solved board games. And maths is somehow a logical game, but played on an infinite board. And so it is naturally the next sort of target. So I've shown you the data. I've shown you some random examples. And for me, they're interesting, but they're not sort of convinced. I'm not convinced that they're going to roll over us right now. I do still feel that in some sense, the systems are still a long way away from what we're actually doing in practice. But what's actually disconcerting is even though they're a long way away, they're moving forwards very, very fast. Everything I've talked about has happened this decade. And so now what will happen, will it continue moving towards us really fast, or will it run out of, sometimes areas run out of steam because, you run into technical problems, theoretical problems that can't be resolved, or maybe it will sort of veer off and we'll get very, very good at some niche area of maths, but sort of not the mainstream. Or maybe it will just steamroller over us all. And it's really difficult to know, but it's just sort of worth thinking about. But certainly it's an interesting time to be a mathematician. So thank you very much. Hey.
Hi. Thank you for the talk. That was...
Thanks for coming.
Yes. So I guess I'm wondering what you imagine a bit more the future looking like. So let's suppose that these systems do end up being able to prove every true statement of length n or something like that. What do we do then? Like, do we just keep building bigger computers and wait for the next interesting statement? Or
I'm an AI pessimist, so I'm not convinced that they will get to. They're very good at generating half-page proofs, but you can't prove the Riemann hypothesis in half a page. You know, the computer scientists are like, oh, Riemann hypothesis in 2 years. But if it takes twice as long to generate a one-page proof, and then twice as long, it just seems. I'm not convinced they're going to. I actually don't think we've got that much to worry about, really. I just think it makes a good talk. So it's my personal opinion. But the reason I give the talk is I talk to computer scientists, and they're deadly serious, and these people are not idiots. Originally, I was writing them all off as idiots, and then I realized that they were sort of experts in the field. So I'm not the best. Are there any computer scientists in the room? Perhaps they could answer the question. I have no real understanding about what's going to happen. All I know is you talk to computer scientists, and they say that we're in real trouble. But, you know, time will tell. I can't. I've told you everything I know, really. I'm going to ask another. Let's have another question, because I don't know the answer to your question. Hello.
Yes, hello. Thank you very much for the talk.
Thank you for coming.
Lovely presentation. I'm curious about this issue of limited training data. You alluded to it in the talk, and indeed, you know, there's work in AI these days on sort of scaling laws, these principles that say, you know, model architectures are about as good now as we need them to be, and now the issue is just getting more data in order to generalize better.
Right.
Yes, and you know, of course, there's a finite number of maths papers, and you know, an even smaller number of truly distinct mathematical arguments. So, you know, I wonder if this approach is to be taken seriously. You know, do you think that there is much more to be gained by training on more papers, or if we've sort of reached the limit of that?
No, I think what's going to happen in the future is there's going to be people, and it's already happening, there's people selling synthetic data. Mm-hmm. People are going to be generating huge amounts of data that computers have generated, and then the other computers are going to train on. I think that's what I think what's going to. Yeah, we've run out of data in some sense. It's difficult to read archive papers, and they've read all of the code written in the. Yeah, we're going to have to figure out. Computer scientists will figure out how to generate many variants of problems. This is my understanding.
So you think the future is in this sort of self-play?
Yeah, it's going to be. That's the point. That's how they beat chess and Go, right? It's going to be self-play in mathematics, and they're going to generate loads and loads of really weird theorems that are sort of not remotely mathematically interesting. 99% of them will be not mathematically interesting, but it will enable the language models to get some kind of feel as to what mathematics looks like and how it works. You know, some feeling that they understand. So that I think that's what will be happening. It's that weird synthetic training data that us humans won't see because it will be all secret. But a lot of things will happen behind closed doors as well, which is extremely frustrating.
So I've got a question about that as well, but if anyone else has got a question, perhaps I'll yield to them first.
Okay. Yeah, I was wondering, do you think that mathematics education, maybe up to the undergrad level, should change given all this? Or what are your thoughts on that?
No. Do you think that? I mean, I teach undergraduates how to use the software, but I'm not suggesting there should be wholesale changes. Yeah, I just think, like, we teach them Python, shouldn't we teach them Lean? But mathematics is so weird anyway. At some level, I think we should absolutely change what's being taught, because, like, why are we teaching? After 3 years of just constantly doing mathematics at my university, my students have learned essentially nothing that's happened since 1940. You know, we prove all these things like finiteness of class group in the hard number theory course, and this was, you know, known to Gauss in many cases and known in the 1850s. So one thing that's very odd about mathematics is we spend all our time teaching people very old stuff, but that's because the new stuff is sort of too difficult to teach. But I don't know. I mean, if computers start being able to, I don't know. The whole question's too hard. I'm not an education specialist.
Ask ChatGPT.
I'm not an education specialist. I already think it's kind of weird how we teach for all sorts of reasons. But yeah, I don't know. I mean, maybe we'll all be unemployed in 10 years' time. We won't be able to teach them anything. So. Or maybe that'll be the only thing we do. Maybe they'll just sack half of us, and the others will just teach classes all the time.
Did you have a second question?
Oh, yes. So the second question I have is that one of the things that human mathematicians are very ingenious at doing is finding new representations, right? Inventing new notation, coming with new ways of thinking about problems. I think this is at the core of the difficulty in mathematics, because oftentimes once you have the right definitions, right, then stating proving the theorem becomes much easier. The IMO problems, right, they sort of come in the right representation already, the sort of elementary algebra. So I'm curious if you have any insight into how good, current, modeling techniques are at finding new representations.
Yeah, I didn't talk about that at all, but I do wonder if they start threatening to prove theorems and make the right conjectures, I wonder whether our job might become finding the right abstractions. Because I didn't talk about that at all, but I've seen no examples of computers coming up with the right abstractions. Things like, how do you prove Fermat's last theorem? It's the same about positive integers, but you prove it using elliptic curves and modular forms. And these kinds of things are very, very hard won. And when you see historically, people have these ideas, modular forms in particular. It took a long time for the right idea to crystallize. And will computers be able to do that? That seems to be very hard.
I see. Thank you.
So, yeah.
Thanks for the talk.
Hey, Brando.
Hey, Kevin. So question. Given the result on the IMO, what do you think is the current level of GPT-01 on the Putnam, for example?
Oh, somebody was telling me that it was doing quite well.
Yeah.
But somebody told me at the reception that it was answering Putnam questions. But the thing that really worries me about this is I've seen papers in computer science before where they say, oh, we've got our language model, and we typed in a question, and it answered it perfectly. And then they print out the answer, and I read it as a professional mathematician and think, well, this isn't perfect. I think this is quite shoddy. I definitely wouldn't give this 10 out of 10. So I worry that if computer scientists come along without mathematicians collaborating with them, they say, oh, we've done the Putnam with our language model with no backing up from a theorem prover. I worry about language models that aren't tied to theorem provers.
Okay.
But I mean, maybe they'll get better. I've just seen too many shoddy answers. I know they'll get better, but they sometimes they just don't. Right? We've all seen examples. They write something, and it's mostly right, but then it's a bit wrong, and then you grill them on the wrong bit, and it just won't get it right. It sort of just tries and tries again, but somehow you really see, you don't actually understand this, do you? You've done quite well, but this bit you can't solve. And you might get hypey papers that say, oh, we've done it, or we've mostly done it. But if you haven't actually done it, then you haven't done it, right? So, yeah, I don't trust O1 yet.
So basically, you think lean is essential for...
I personally, well, I'm a formalist. So I don't like vague. If there's a bit missing in an answer, as far as I'm concerned, it's wrong, right? And so I think that the future is in the hybrid model, but not everybody. I don't think Szegedy does. I don't. So we shall see. But the worry is that you'll just get in 10 years, in a few years' time, if a language model belches out a 30-page proof of the Riemann hypothesis, then if it gets to the point where you can just press a button and get a 30-page thing that looks like a proof of the Riemann hypothesis, then you'll just get people spamming the journals with them. That would be sort of terrifying, nightmare. And none of them will be right, but they'll all be mostly right. And so I'm sort of dreading that. Hello.
Hi, thank you. I'm curious, because one of the things you talked about was that currently it might, or in the future it might veer off track, get into niche areas of mathematics.
Maybe.
Are there certain categories of math where it seems to kind of do better than others?
Right.
And likewise, are there certain groups of mathematicians that are more amenable to using AI?
I don't quite have enough data to answer that. I know when it comes to formalizing mathematics, there's definitely some areas that are easier to formalize in the sense that to make progress in these areas, you have to be very smart and put things together in the right way. But you just sort of, the objects being used are sort of undergraduate level objects. But the assembly is the genius part. So when it comes to translating mathematics into lean, there's definitely some areas of mathematics which are much easier than others. And whether that will translate to those areas being easier for AI, I don't really, I mean, we haven't really had AI sort of attacking modern research problems yet. But yeah, again, these are hard questions, by the way. It's a terrifying audience. But somehow I've given the talk too early. In a few years' time, I'll have a lot more data. But it might, my experience with theorem provers is that yes, there's definitely some areas of mathematics which are easier to formalize than others. And so maybe there could well be areas of mathematics which are easier to... Well, I mean, these AI techniques for finding conjectures, you need tables. And there's some areas of maths where there aren't any tables. There's like uncountably many objects and you can't even arrange them in an order, let alone make tables of them. So, you know, the table stuff is sort of definitely limited to areas of maths where you can say, here's my list of objects. They're in a nice list and here's some numbers attached to them. Yeah, no, I'll put it in the diary.
So I think we can take the three questions, three people who are standing here.
Oh, no one else is allowed to stand up.
So, please.
Yes, it's very similar to the other one.
Uh-oh. I couldn't answer that one.
Okay.
Go on.
So for lean, there are problems, for example, in PDEs or geometry where
Yeah?
it feels very difficult to formalize into lean.
Yeah.
Is this actually an issue, or can you actually do this?
No, that's a sociological problem. I've been pushing the software, and I've learned very quickly that the way to make people interested in the software is to sort of attacking modern problems, and so I've been attacking modern problems in my area, and then people in my area come and start using the software. And there's not sort of an analog, and I'm a very discrete mathematician, and you're mentioning sort of continuous mathematics. And there's not sort of an analog of me that's sort of doing, there have been plenty of things, like they proved sphere inversion in lean, you could turn a sphere inside out, but that's a theorem from the 50s, you see. And what I've just noticed empirically is that what people find really exciting is sort of mathematics that was done in the last few years. And so all we need is for someone to come along and start doing, you know, some recent theorem in PDEs, then there'll be a flood of PDE people coming in. So it's just sociological at the minute. I don't think there's any intrinsic difficulty in doing PDEs. The fact that they're not being done is just some sort of historical fluke.
Thank you.
I hope. I believe as well.
Hi, thanks
Hi.
for the talk.
Thank you for coming.
My question is, so I think I noticed that perhaps there's a fourth step that is missed in your steps. It's understanding the proof. Right?
Oh, yeah.
Humans generating the proof. Humans can understand it. I'm wondering, you know, as if a model spits out a 30-page potential proof of the Riemann hypothesis, how do we know that it is? And then how do we know what that means? How do we translate it back into human understanding?
Are you talking about spitting out a computer program, spitting out a lean?
Spitting out a
code?
lean, yeah. Or spitting out some proof. How do we understand what these models have come to say? And then I guess a follow-up to that is in your experience, is mathematics more about the answer to the question or the reasoning to get to that answer? Yeah.
I mean, mathematicians have very different views on this question. And I'll give you my personal view because I'm the guy standing at the front, but there'll be plenty of other people who will disagree completely. I personally would really love to see a computer spitting out an incomprehensible 1 million line long proof of the Riemann hypothesis that nobody could understand at all, because I just think that would be really funny. It would just... It would be like there was a lot of fuss with Apple and Harkin. They proved the four-color theorem, and the proof was not sort of human understandable because it sort of reduced it to a very large calculation that couldn't fit into a human's brain. And there was a lot of fuss about that. And so, you know, it could be Apple and Harkin too. And I just, because I like the idea of disruption, right? One of the reasons I'm in this game is because I want to disrupt mathematics. And I think this would be a really, really good way of disrupting it. So I'm all for it, but other people would be horrified. I'm sure there'll be many people in this room that you know, I know people that find this whole thing abhorrent because they're sort of scared of that, whereas I'm absolutely welcoming it because, you know, I just want to know the answer, right? I don't know. So sorry. to most people. But that's
Our last question.
hello.
Hi, thank you for the talk. Actually, a very similar question is there's multiple different ways to prove things. Like, there's a bunch of different proofs of the Pythagorean theorem, or even like the infinite prime numbers, and you can make an argument that some are like more beautiful than others.
Oh yeah.
And so I'm curious, like in a future where computers make a proof of something, would you do you believe there's still an argument to try to prove that ourselves in hopes of getting a more beautiful proof for it?
Maybe
Or
that's
do
what
you
humans will end up doing. Because we've certainly, although ironically, having just been very rude about human proofs and saying that any proof will do, when you're formalizing mathematics, formalizing a grotty, ugly proof is much harder work than formalizing a conceptual proof. And one of the things you do is you look at the definitions and you look at the arguments, you think, are these written in the right generality? Because when you abstract something and write it in the right generality, it can be sort of much easier to work with. So having just, I'll completely contradict what I just said over there. One of the reasons I'm currently working on a proof of Fermat's last theorem, and I'm really hoping that by the end of it, we've made the proof more beautiful. But this is human. This is not AI. This is human translation. But we want to sort of look at the arguments and try to work out what they should say, because it's certainly the case in the literature that many times people don't write the most correct abstract conceptual arguments. And we've seen this several times many times in Lean's maths library. We have definitions which are cleaner and work in more generality. And they're original research, but nothing's published. They're just all written down in our library. So I would argue that sometimes formalizing mathematics can make it more beautiful, which is sort of different, like, because you were sort of saying, what about humans trying to beat... I'm not talking about AI. I'm talking, yeah. If AI makes ugly proofs, then humans can try and cheer them up. But at the minute, this manual thing, which I still consider an art in some form. So clearly, I must have some sense of beauty. And actually, I think I've just got a sense of laziness, because formalizing crappy proofs is hard work, and formalizing beautiful proofs is really nice. So,
Thank you.
There you go.
Okay, so we have an encore question. Okay.
Oh, sorry, super short question. My question is, for this Lean community, those people trying to formalize those proofs, like, are they mostly in the UK and US? Like, are there people from
mostly in UK
other
and Europe.
countries and just like random places in the world? Like, how would you describe this community? Where are
they're
they
mostly in the UK and France and other places in Europe. And I don't really understand why that's the case. There's been very, very low uptake in the US, which surprises me, because actually what's happening is a lot of the money is coming from the US now. There's far fewer people, but there's far more money. So I think that the US is sort of trying to buy. Maybe things will change, but yeah, right now Europe is winning hands down. So you're missing out on the future, you people. You might want to reconsider your hiring strategy.
Okay.
I see. You're being poached by the tech companies. Yeah, okay. Yeah.
So I would like to thank our speaker for the great lecture and our audience for all the questions. And we'll return with another public lecture in the not too distant future, sometime in early next year. And maybe we'll have our speaker back in a few more years with updates on AI and proofs.